Hello and welcome back to Trigonometry, MAT 155. In this lecture, we're going to be dealing with operations on and alternate forms of vectors. So as mentioned in the previous part of section 5.4, we talked that we can add vectors, we can multiply by scalars on the outside, and we also talked about how these vectors can be written sort of algebraically. So addition works pretty much exactly like you would think algebraically. Like you got the component y's, the horizontal components add, the vertical components add. So x plus y, y plus b, or x plus a, y plus b. We can also take the scalar that's on the outside and multiply it to each of the components inside. All right. So what if we saw something like the vector v being 3, 2, the vector w being negative 4, 7, and we're trying to find the resultant vector from 3 times v, the scalar 3 times v, minus 2 times w. So what would we do? Well, it's the same as multiplying, so 3 is the scalar, 3, 2. Let's just rewrite it in their forms. Minus 2 times v, which is negative 4, 7. We can multiply, so that's 3 times 3, and then 3 times 2. For this first one, so 3 times 3, 3 times 2. And then we can take the negative with the 2, so we're actually adding. So negative, so we have negative 2 times negative 4, comma, negative 2 times 7. Oops, negative 2 times 7. And so we get 9. 3 times 3 is 9. 3 times 2 is 6. Negative 2 times negative 4 is positive 8. Negative 2 times 7 is negative 14. And then we can just simply add 9 plus 8. So add the horizontal components and then add the vertical components. Comma 6 minus 14. And when we compute this, 9 plus 8 is 17. 6 minus 14 is negative 8. Box our answer. Now, it turns out that dealing with this notation can be sometimes a little bit cumbersome, maybe even unnatural. And a lot of people want to look at things sort of how they're used to dealing with them. And to do this, if we define I as 1, 0 and j, or I hat, excuse me, as 1, 0, and this j hat as 0, 1, then we can decompose and rewrite the vector. Basically, instead of writing it like this, we have these things kind of built in, but we've kind of condensed them to an I hat and a j hat, where I hat is only stuff next to I hat only deals with horizontal components, and the j hat stuff only deals with vertical components. Horizontal components for I hat, vertical components for j hat. And we can decompose this as the a, which is the horizontal component. So a times I hat plus b times j hat. And people would a lot of times typically prefer to deal with this. Now, before we do some computations, really quick, just note that this I hat, there's a bunch of different ways we can do this. I could, instead of putting the hat over it, we could have put an arrow like other vectors. We could have made them bold instead. But in this text, we're going to do this, or in this lecture series, we're going to be doing it with the hats, because first off, it's equivalent, and second off, if I used I, sometimes people confuse that for I as the square root of negative 1, and we do this as just a nice way to distinguish more. In the context of what's going on, you can usually decipher, because mostly you'd probably need a j hat, but not necessarily, but you can usually distinguish with context, but here it just makes it that much easier to quickly tell what you're dealing with. You see the hat, you're dealing with vector components, that's it, versus I, you're dealing with actual complex numbers like we did back in 5.3. So let's just get back to some more computations of resultant vectors. So here, 2v minus w, that's 2 times v, which is, instead of writing it, like that, let's multiply it by 2 I hat plus 3 j hat. And then minus w is 3 I hat minus 4 j hat. And the immediate benefit of this notation is it feels more familiar. You got the 2 I hat, so that becomes, so you just distribute this and you get 4 I hat plus 6 j hat, distribute the negative, so you get minus 3 I hat plus 4 j hat. And then you can just combine like terms. So the I hats would be like terms, and the j hats would be like terms. 4 I hat minus 3 I hat is just 1 I hat, or just I hat. And then 6 j hat plus 4 j hat is 10 j hat, which is fine, but you can also just rewrite it like this. I hat plus 10 j hat. Further, we have, if we just multiply by a scalar, again, still more what we're used to, 3 I hat minus 4 j hat. We get 9 I hat minus 12 j hat. And then we can also talk, so again, bringing it back, if I said, hey, what is the magnitude of this guy? We now have a different way to think about him, but it's still the same idea. So we're trying to find the magnitude of this, and that's still the horizontal component squared. So 2 squared plus the vertical component, 3 squared. So we get 4 plus 9. And we have the, ultimately we have that the magnitude of our vector is just the square root of 13. All right. Now, as it turns out, just a little housekeeping, we can also talk about some vectors being a little bit special. And that's because their magnitude is 1. Basically from the origin, so we can think about this being from the origin to wherever it's going to have a magnitude of 1. And we call these in particular unit vectors. And usually instead of saying v, we'll usually use something like u. Though it's not always needed. Why do we talk about this? Well, as it turns out, sometimes we may only want to think about the direction. So being a unit, we know that the magnitude's always 1, it basically just tells us the direction. And we may want to know how to find it. So there's two sort of competing ideas that come from this. The first one is, what if I just want to find the unit vector? Well, as it turns out, we can define the unit vector as being, of the particular function, as being the vector divided by the magnitude. Now remember, the magnitude is a scalar, I mean it's just a number, and so you could then distribute to both the components, right? So basically divide it into each component is kind of what that's suggesting. So, or multiply by 1 over the magnitude to each component. So the other idea, if you just multiply both sides by the magnitude of the vector, this means that you can rewrite the vector as the magnitude of the vector times the unit vector. Okay? So, and that's an idea we're going to come back to here in just a moment, but let's do a computation. So let's talk about if we want to find the unit vector of this guy. So what do we have to do? Well, we need to find the magnitude. That's the first thing. So the magnitude of our particular vector v, it's just the square root of 4 squared plus negative 3 squared, which is 16 plus 9, which is 25, which is just equal to 5. All right? So then what we're going to do is we're going to take our unit vector then will be 1/5 of our vector. So our vector is 4, so we just 1 divided by this, or we can just divide it into it. It might make some people happier to think about that way. So 4 I hat, so 1/5 times 4 I hat minus 3 j hat. And then we can just distribute the 1/5. So 1/5 times, remember, fraction times a whole number, you can just multiply straight up to the top. So 1/5 times 4 is 4/5. Negative 3 times 1/5 is negative 3/5. So we end up getting 4/5 I hat minus 3/5 j hat. And this 4/5 I hat plus, or minus rather 3/5 j hat is a unit vector. Okay? Now, so that's how we find a unit vector if we want. But why might we want to talk about it? Well, as it turns out, and why might we want to decompose a vector to be the magnitude times the unit vector? Well, remember that even though these kind of give us a direction, we go left or right that much and up or down that much, in this case, right 4/5, down 3/5, it may not, it requires two sort of thoughts to get the direction. Further, we're in trig. How do we talk about direction? Well, where does the angle point? And that's what we're going to do, or talk about. So we have a horizontal and vertical component, so we can talk about x's and y's. And when you think about that, we can think about triangles, and we get this thing called a direction angle for the vector. So we get then a magnitude and a direction, and the thought is sort of complete with what a vector is. We can rewrite basically every vector as the magnitude times cosine theta for the horizontal components plus sine theta for the vertical components. All right, so what do we do? So if I'm just given a vector, how can I find the direction angle? Well, again, we can think about this as an x and as a y. So the x being, in particular, I'll come back down here and I'll say x equals 4. And again, don't forget to include the direction, y being negative 4. And we can think about tangent. So we got y's and x's. Tangent of theta is y over x, or in this case, negative 4 over positive 4. That simplifies to negative 1. So where is tangent of theta negative 1? Well, the sort of reference angle is pi over 4. So that's where sine and cosine are the same, which basically make the tangent being sine over cosine be equal to 1. But that's the reference angle. That's if we didn't have to deal with a positive or negative. But 4 being, so we have a horizontal component being to the right 4. 1, 2, 3, 4, and down 4. 1, 2, 3. 1, 2, 3, 4. Then we can think about this as being in the fourth quadrant. So we can simply, since we don't have to necessarily worry about the angle, we can talk about negative angles. So we can talk about the direction angle being negative pi over 4. And if you really want to, you can think about this being positive. So you can think about it being between 0 and 2 pi being, so not equal, but technically, but would give us the same output, would be, for tangent, 11 pi over 4. All right. I'll say negative pi over 4 is simple enough, but depending on the situation, what you might want. All right, that concludes everything for this section on vectors.